Okay, so now that we've discussed elementary row operations, we're now in a position to talk about the Smith normal form, which is a way to use elementary row operations to transform the boundary matrix into a form which reveals its rank, its eigenproperties, which then allows us to compute, amongst other things, it's like the rank of the the boundaries, it's like of the cycles, it's like, and as a consequence, it's like the Betti numbers. Okay. All right. So this is what is called Smith normal form. So using sort of these row and column operations which we discussed before, all right, we can reduce the P boundary operator, P boundary matrix, to what is called Smith normal form. Okay, and again, as before, we're going to specialize the case where we're just doing Z2 arithmetic, right, or modulo 2 arithmetic. This is quite simple. This means that you have an initial segment of the matrix where you have a diagonal component, right? Which is 1, and everything else is 0. Okay, so it's a very, very simple form. So let me sort of just draw it out for you in a block to give you a sense as to what's going on. Okay, so there's going to be basically a square block here where these entries are just 1s. Okay, and everything else, it's like the matrix is 0. Okay, so what's significant about this? Okay, so this part here is the rank of the boundaries of P minus 1. Okay, so this is the rank of the chain group of dimension P minus 1. Right, this is the rank of the chain group of dimension P. Right, and then this piece here is the rank of the cycles of dimension P. Okay, so cycles, if you recall, the things which map to 0, it's like under the boundary operator, right? And then, the boundaries obviously are the are the things, it's like, which are in the image, it's like of the boundary operator. Okay, so hopefully it's clear why that's the case. All right, so in any case, right, so that tells you a whole bunch of things. You see, the point, of course, is that what happens with the Smith normal form is that it really tells you this rank BP minus 1, right? But you also know the rank of CP minus 1 and the rank of CP. It's like just because of the way you've constructed, it's like the boundary operator, it requires you, amongst other things, to enumerate all the P simplices and P minus 1 simplices and so on. So you know this, you can get this rank BP minus 1 from this, the number of 1s here. And you can also get a rank of ZP, it's like by taking the rank of CP and subtracting off the number of 1s, right? So now you know the rank of ZP, you know the rank of BP minus 1, and obviously that's all you need in order to compute the Betti numbers, right? So that's exactly the situation you have. So you know that NP is equal to BP minus 1 plus CP, right? Actually, this, yeah. So again, the point is that, so these are the things which give you the non-zero boundaries, right? So this column of ones is like, sorry, this diagonal ones give you the non-zero boundaries. So that's gives you the BP minus 1. So the leftmost BP minus 1 columns, right, have ones along the diagonal. And the rightmost columns. Zero. So the former represent the P chains whose non-zero boundaries generate the group of P minus 1 boundaries, right? And then the latter sort of get mapped to 0, so obviously they are cycles. Okay, so again, this is an explanation as to why this thing gives you the rank of BP minus 1, and then this gives you the rank of ZP. Okay. All right. Okay. So once you have everything in Smith normal form, right, you know exactly rank of BP minus 1 and the rank of ZP. Okay. So obviously now you're in a position to write down the Betti numbers, right? So from Smith normal form, and knowing the rank of the chain groups, right? We can get the rank of BP minus 1. Well, actually, you need to combine its like information from multiple boundary matrices, right? Because, yeah, and the rank of ZP, right, for all P, right? So from this, right, the Betti numbers are just given by beta P is equal to the rank of ZP minus the rank of BP, right? So we're not quite done yet because, you know, as important as it is to know the rank, it's like of the homology group, it's also helpful to know what is the basis, it's like, which gives you these things, right? So if you recall, right, we said that the row operations, okay, the row operations essentially would transform, it's like this boundary matrix, okay, but you could interpret the row operations as something which is acting on the basis as well, okay. So what do I really mean by that, right? So So what is going to happen is that you're going to get this normal form. Let's call it NP for this. Okay, so NP is going to be the Smith normal form for the P boundary matrix. Oh, okay, and I'm going to write this. It's like as U P minus 1 times the boundary operator times VP. Okay, so again, if you recall, it's like we're going to take this boundary matrix and we're going to perform these row and column operations so that it ends up into Smith normal form. But the way you can interpret these row and column operations is by left multiplication, it's like by a matrix, and right multiplication by a matrix. Okay, so another way to sort of think about this is that you could have first started off with two identity matrices on either side acting on boundary P, so that's the original matrix representation, and as you transform this boundary P, you also sort of keep track of what you're really doing in terms of these addition operations, in terms of rows and columns, and sort of row and column exchanges in these UP minus 1 and VP sort of matrices. And then what's going to happen is that when you've finally done everything, it's like then these UP minus 1 and VP is going to tell you what is the basis for the P simplices and the P minus 1 simplices, which cause this matrix, the original boundary matrix, which is expressed originally in terms of this prescribed ordering of the simplices, into something which now is in Smith normal form. Okay, and then that's going to be the stuff it's like which is going to be helpful. So okay, so the point is that the new basis. So okay, so I should say that you might want to sort of determine a basis for the cycle and boundary operators, for the cycle and boundary groups. Okay, and the point basically is that the basis, or the new basis, if you will, for the cycle group is given by the last ZP columns of VP. All right, and then similarly the new basis for the boundary group is encoded in the first BP minus 1 columns of the inverse. Of UP minus 1. Okay? All right. So anyway, so yeah, so you can look at these elementary operations and then figure out how to get something which you want. So I should say that it's like you might think, oh, we have to compute the inverse of UP minus 1. That would be nasty. As it turns out, it's not so bad, right? Because if you recall, it's like if you do row or column exchanges, it's like, and you add, it's like columns to other columns or rows to other rows, right? Then the inverses are essentially, it's like related, can also be expressed in terms of these kind of elementary row and column operations. So if you keep track of what you got what got you to this UP minus 1 in particular, the sequence, it's like of exchanges, it's like all additions, you can invert that, it's like term by term, right? So actually computing that inverse is actually not so bad because you can, again, if you keep track of this, you can actually construct the inverse. It's like as you are assembling UP minus 1 as well, okay? All right, so again, this gives you a high-level picture. It's like what the Smith normal form is. And the next thing we'll do is that we'll present an algorithm for actually converting this boundary matrix into Smith normal form. Okay, so let me just stop here for now.